All right, let's jump right in. We're taking a deep dive into quantum computing today. Everyone's talking about it, but it can be kind of tough to wrap your head around, so that's what we're here for.
Absolutely. It's definitely one of those things that sounds like it's straight out of Star Trek, right?
Yeah, it does. I mean, when I hear quantum, I think like tiny particles and weird physics stuff.
Exactly.
Yeah.
And it is about that, but it's also about solving some seriously big problems that regular computers just can't handle.
Okay, so before we go any further, can we break down the basics? Like, what's the big difference between a regular computer and a quantum computer?
Well, at the heart of it, it's all about bits versus qubits.
Okay, so a bit, that's like the ones and needs that our computers use now, right?
Yeah. Think of a bit like a light switch. It's either on or off, 1 or 0. But a qubit, now that's where things get interesting.
How so?
A qubit can be both 0 and 1 at the same time, thanks to something called superposition.
Wait, hold on. How can something be in two states at once? That's like saying a coin is both heads and tails before you flip it.
You got it. That's a great analogy. It's like that coin spinning in the air, holding both possibilities until it lands. That's superposition.
Okay, so one qubit can be doing two calculations at the same time. I think I'm starting to see why people are so excited about this.
Exactly. And the craziest part is, as you add more qubits, this power grows exponentially. 2 qubits can be in 4 states at once, 3 qubits in 8 states, and it just keeps going up from there.
Whoa, that's wild. Okay, but I keep hearing that quantum computers aren't going to replace our laptops anytime soon. Why is that? I mean, if they're so powerful.
It's because they're not meant to be general-purpose machines like our laptops. They're really good at specific types of problems that classical computers just choke on.
Okay, I see. Like what?
Well, think about factoring really, really big numbers. The kind that are used in encryption, keeping our online information safe.
Right, right. I think I read about this in one of the articles, Shor's algorithm.
Yeah, Shor's algorithm is a quantum algorithm that's specifically designed to factor large numbers, and it does it exponentially faster than any classical algorithm.
So what you're saying is someone with a quantum computer could use this Shor's algorithm to break the codes that protect, like, our online banking and stuff.
It's a possibility, yeah. It's why cybersecurity folks are working hard to develop new encryption methods that can stand up to quantum computers.
So it's like a race against time, kind of?
You could say that.
Hmm.
It's a constant back and forth between making codes stronger and developing new ways to break them.
That's intense. So besides breaking codes, what else are these quantum algorithms good for?
Well, there's another one called Grover's algorithm, and this one's all about searching through massive amounts of data.
Okay, data searching, like how is that different from what Google does now?
Imagine you're trying to find a specific grain of sand on a beach. A regular computer would have to look at each grain, one by one. But Grover's algorithm can search much, much faster by using these weird quantum properties.
So it's like a super-powered search engine.
Exactly. This could be a game changer for things like drug discovery, where scientists are searching for very specific molecules.
Oh, so instead of taking years to develop new medicines, we could do it way faster with quantum computers.
Potentially, yeah. And not just that, it could revolutionize everything from material science to finance. But we'll get to those in a bit.
This is already blowing my mind, and we've only just started. Okay, so we've got these qubits, and we've got these powerful algorithms. But what about the underlying quantum mechanics principles? What's the deal with this thing called entanglement? It sounds kind of spooky.
Well, it is kind of spooky. Imagine you have 2 qubits, right? And they're linked, entangled, in such a way that even if you separate them by a huge distance, they still act like they're connected. You change one, and the other one changes instantly.
Whoa, that's like telepathy or something. How is that even possible?
It's one of the biggest mysteries in quantum mechanics. Even Einstein called it spooky action at a distance. But it's this entanglement that allows qubits to work together in ways that regular bits just can't.
Okay, I think I'm getting it. So entanglement is like the secret sauce that makes quantum computers so powerful.
You could say that. And then there's this thing called quantum interference.
Quantum interference, what's that all about?
Think about waves in the ocean. Sometimes they add up and make a bigger wave, and sometimes they cancel each other out. Well, quantum interference is kind of like that. Quantum algorithms use this wave-like behavior of qubits to figure out the right answers faster.
So it's like using the weirdness of quantum mechanics to get to the solution quicker.
You got it. And all of this is happening at the subatomic level,
Yeah.
which is just mind-blowing when you really think about it.
This is a lot to take in. But I'm starting to see how all these pieces fit together. We've got the qubits, the algorithms, and the mind-bending quantum mechanics principles.
Exactly. And it's all coming together to create this whole new realm of computing that has the potential to change the world as we know it.
I'm definitely hooked. All right, well, we've covered a lot of ground here, but I feel like we're just scratching the surface.
Oh, we are just getting started. In the next part, we'll dive deeper into the real-world applications of quantum computing and see how this technology is already starting to make an impact.
Sounds good to me. Can't wait. Welcome back to our deep dive into quantum computing. So last time, we were talking about entanglement and how it's this kind of spooky connection between qubits. It sounds amazing, but building a quantum computer can't be easy, right? What are some of the challenges they're running into?
Oh, there are a bunch. One of the big ones is just keeping those qubits in their superposition state. Remember, they need to be both 0 and 1 at the same time to do all that quantum magic.
Right, like that spinning coin analogy. But the articles we read said that keeping them in superposition is super hard. What's knocking them out of whack?
Well, think of it this way. Qubits are incredibly sensitive. Even tiny things like vibrations, temperature changes, even a stray magnetic field can mess them up.
Wow, so it's like trying to keep a house of cards standing up in a windstorm. What are they doing to try and create a more stable environment?
They're getting really clever. Some researchers are using these superconductors, materials that have zero electrical resistance, and they have to cool them down to ridiculously low temperatures. It's like creating these super chilled zones where the qubits can just chill out.
So they're like giving the qubits their own little Zen gardens.
Yeah, something like that.
Yeah.
Other researchers are using trapped ions. They're suspending single atoms in a vacuum chamber. This isolates them and helps them hold onto their quantum state longer.
Wow, that's amazing. But even with all those precautions, the sources mentioned that quantum computers still have a lot of errors. How do they deal with that?
That's a huge challenge. Even a tiny mistake in a quantum calculation can cascade through the whole system and make the results totally worthless.
Oh, so it's like one little mistake can snowball into a giant mess.
Exactly. So they're coming up with these really smart error correction techniques. It's like weaving in backups for the quantum information, so even if some qubits mess up, the calculation can still keep going.
It's like having a safety net for the quantum computer, right? So we talked about stability and errors. But what about scale? Most quantum computers now only have a handful of qubits. What needs to happen to get to hundreds or even thousands of qubits?
That's the million-dollar question. Scaling up is essential if we want to solve those really complex problems we talked about before.
Going from a few qubits to thousands, that sounds like a pretty massive jump.
It's a huge jump, but there are different approaches they're trying. Some researchers are working on these modular systems where they connect smaller quantum processors together.
Oh, so it's like building a giant quantum computer out of smaller building blocks?
Exactly. It's like Legos, but way more complicated. Another approach is to use photons, which are particles of light, as qubits. Photons are super stable and can travel long distances without losing their quantum properties.
Oh, so you could create a quantum internet where information is zipping around at the speed of light.
That's the idea. And the really exciting thing is that quantum computing is still such a young field. We've barely scratched the surface of what's possible.
It's mind-blowing to think that all this is happening at the subatomic level. It's like we're harnessing the fundamental building blocks of the universe to create these incredible machines.
It really is. It's not just about building faster computers. It's about opening up a whole new world of possibilities.
Well said. So we've talked about challenges, crazy concepts, and this whole idea of scaling up. But I'm really curious to hear about the real-world stuff. Where is all of this actually being applied today?
That's a great question. We're going to dive into some really cool practical applications next. Get ready to see how this quantum revolution is already starting to make a difference in fields like medicine, materials science, and even artificial intelligence.
Awesome. I can't wait to hear about it.
Right.
Okay, so let's get into the real-world stuff. Where are we actually seeing quantum computing being used today?
Well, get ready for some seriously cool applications.
I'm all ears. Let's start with medicine. I remember you mentioned drug discovery. How's quantum computing speeding things up there?
Imagine trying to design a new drug. It's super complicated. You need to understand how different molecules are going to interact with each other, and that's where quantum computers shine.
Because they can simulate those interactions, right?
Exactly. Classical computers struggle with that kind of simulation, but quantum computers can handle it with incredible precision.
So instead of spending years in the lab mixing and testing different chemicals, researchers could use a quantum computer to run those experiments virtually.
You got it. It's like having a virtual lab where you can try out tons of possibilities way faster.
That's amazing. It's like fast-forwarding medical breakthroughs. But what about beyond drug discovery? What other possibilities are there in
I
medicine?
was thinking about medical imaging, MRI scans, CT scans, all that stuff.
Yeah, yeah.
They can be kind of blurry sometimes or not show enough detail, but quantum computers could help us get much clearer images, even down to the molecular level.
So it's like having a quantum microscope for the human body.
Exactly. We could detect diseases way earlier, maybe even before symptoms show up.
Hmm.
And it's not just medicine. Quantum computing is going to be huge for material science, too.
Oh, yeah, right. We talked about how these quantum computers can manipulate things at the atomic level. So what kind of impact could that have?
Imagine being able to design materials, atom by atom, and give them specific properties. We could create materials that are way lighter but also stronger, or materials that conduct electricity perfectly at room temperature.
Okay, now that would be revolutionary. We could make everything from airplanes to electronics more efficient and powerful.
Absolutely. Stuff that used to be science fiction is becoming a reality.
This is incredible. What about finance? Didn't we read that quantum computers could really shake things up there?
Yeah, finance relies on some pretty intense calculations, things like risk assessment and optimizing investment portfolios.
Right, right.
Quantum computers could do those calculations way faster and more accurately.
So it's like having a crystal ball for the stock market.
Kind of. It could really change the way we make financial decisions. And speaking of shaking things up, let's not forget about artificial intelligence.
Oh yeah, AI, I almost forgot. Didn't our sources say that quantum computers could supercharge AI algorithms?
Absolutely. We're talking about AI that can analyze massive amounts of data and learn at an insane speed. We could solve problems that are way too hard for even the most powerful computers we have now.
So we're talking about AI that could speed up scientific research, personalize education, maybe even create art and music that rivals what humans can do.
Exactly. Quantum computers could unlock whole new levels of intelligence and creativity in AI.
Wow, this is mind-blowing. It seems like quantum computing could really touch every part of our lives. It's a true revolution.
It really is.
Yeah.
But we're still in the early stages. A lot of these applications are still
Yeah.
being developed, and there's still some big challenges to figure out.
That's true. But it feels like things are moving so fast. Every new breakthrough gets us closer to seeing the full potential of this technology.
Absolutely. It's such an exciting time to be watching this quantum revolution unfold.
It really is. We've come a long way in just this deep dive, from the basic ideas to these amazing real-world applications.
And who knows what's next? Quantum computing is full of surprises.
It's a good reminder that we live in a universe that's full of possibilities. I mean, who would have thought that we could harness the power of these tiny particles to do such incredible things?
Exactly. And maybe someone listening right now will be the one to make the next big quantum leap. So keep learning, keep exploring, and keep that sense of wonder alive. Because the future of quantum is just beginning.
Well said. And that's a wrap for our deep dive into quantum computing. Thanks for joining us.